Welcome to The Explainer. Today, we are taking on a topic that separates the top-tier students from the rest in the Cambridge Mathematics 0580 exam. We are talking about linear programming. Now, in your exam, you have to make split-second decisions, right? You need to invest your time where the marks are highest. And this topic, this is a massive point score. At its core, linear programming is all about limitations. You only have so much time in a day, a business only has so much money in its budget, and a factory only has so much raw material. But how do you make the absolute best choice when you are boxed in by all of these different rules and constraints? Well, you don't just guess, you draw it. Today, we're going to learn how to translate real-world limitations from plain English into actionable visual graphs. We will literally be drawing the boundaries of what is possible, creating a visual safe zone where the perfect solutions live. So whether you are aiming to crush that Cambridge math paper or you just want to understand the logic behind complex logistics, this is an absolute mathematical superpower. Okay, let's dive into this. Here is our roadmap for today's strategy session. 1. Decoding inequality symbols. 2. Graphing single boundaries. 3. Testing the regions. 4. Combining multiple constraints. And 5. Real-world linear programming. Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 1. Decoding inequality symbols. Learning the language of limits. To build our visual maps, we first need to understand the language. Mathematics is essentially a foreign language, and treating this table as a direct, no-nonsense translation guide is the secret to mastering linear programming. You've probably seen these symbols before, but let's lock them in, because examiners love testing your precision here. If you don't get this translation right, your whole graph will be upside down. The open mouth of the symbol always points to the larger value. So our first symbol, pointing to the right, means is greater than. If we say x is greater than 5, x absolutely cannot be 5. It must be 6, 7, 8, or even 5.001. The second symbol adds a little horizontal line underneath. That line is actually half of an equal sign, so this means is greater than or equal to. If x is greater than or equal to 5, then 5 is perfectly acceptable. Moving down, the symbol pointing left means is less than. And finally, with the line underneath, it means is less than or equal to. When you encounter word problems later, phrases like a maximum of will translate to less than or equal to, while at least translates to greater than or equal to. Memorize this translation guide because these four symbols are the architects of everything we're about to build. Section 2. Graphing single boundaries. Drawing the fences. Now that we know our symbols, we can get visual. This is where you really start picking up marks. Those mathematical symbols we just decoded, they literally draw boundaries, or fences, on a coordinate graph. They take an infinite grid of possibilities and chop it right in half, separating the numbers that work from the numbers that don't. Now, there is a crucial visual rule you absolutely must follow when drawing these fences. If your inequality is strict, meaning it uses a less than or greater than symbol without that little line underneath, you must draw your boundary as a broken or dashed line. Think of a dashed line like an invisible electric fence. You can get incredibly close to it, but you cannot touch the line itself. The line is not part of the solution. On the flip side, if your inequality is inclusive, meaning it's less than or equal to or greater than or equal to, you draw a solid line. A solid line means the boundary itself is physically part of the safe zone. The fence itself is included in your solution. Getting this right is absolutely critical. Drawing a solid line instead of a dashed line in your exam will literally cost you points. Section 3. Testing the regions, finding the safe zone. So, you've translated your symbol and you've drawn your line on the graph, either solid or dashed. But a line just splits the graph into two halves. Now we have to figure out which side of that boundary actually satisfies our mathematical rule and which side we need to ignore. We need to find the safe zone. To figure that out, we use the random coordinate test. It's a simple, foolproof, three-step method. Step 1. Choose any random coordinate point on the graph, as long as it does not sit exactly on the line you just drew. A great pro tip for saving time is to use 0, 0 if your line doesn't pass through it, because zeros are incredibly fast to calculate. But let's say we pick the coordinate free 1. That means our x is 3 and our y is 1. Step 2. Substitute those exact values into original inequality. Let's imagine our rule was y is less than or equal to x plus 2. We plug in 1 for y and 3 for x. Our equation becomes, is 1 less than or equal to 3 plus 2? Step 3. Evaluate it. That simplifies to, is 1 less than or equal to 5? Yes, it absolutely is. Because the statement is true, the entire side of the line where the point 31 lives is your safe zone. It satisfies the inequality. A quick note on convention here. Some exam papers ask you to shade the region that works. Others ask you to shade out the unwanted region, leaving the true solution area clean and unshaded so it's easier for the examiner to read. Always read the specific instructions carefully, but the testing math remains exactly the same. Section 4. Combining multiple constraints. Layering the rules. And hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's get back into it. We've mastered a single rule. But let's be honest, reality and your exam paper is rarely that simple. We need to shift our focus to what happens when we have several competing rules at the exact same time. This is how the real world actually works. A factory doesn't just have one constraint, they have a budget limit, a material limit, and a time limit. We have to layer these rules. So the crucial point is this: our goal is to find the ultimate common ground. We are looking for a solution that satisfies all the inequalities simultaneously. Imagine graphing one rule and crossing out the bad area. Then you graph a second rule and cross out its bad area, then a third. You're progressively shrinking the viable space on your graph. The final solution is that one specific region that survives every single boundary we draw. It's the area left completely unshaded by all the restrictions combined. Let's move to a visual example and see how this builds, layering 4 specific inequalities one by one. First, we draw x is less than or equal to 2. We draw a solid vertical line at x equals 2, and we eliminate everything to the right of it. Our world is now just the left side of the graph. Next, y is greater than -1. Notice this is a strict inequality. We draw a dashed horizontal line at y equals -1 and cross out everything below it. Our viable space is now just a corner. Third rule, y is less than or equal to 3. A solid horizontal line at y equals 3. We cross out everything above it. Now our safe space is a rectangle, boxed in on 3 sides. Finally, the slanted roof. Y is less than or equal to x plus 2. We draw this solid diagonal line, test a point, and eliminate the area above the slant. What we are left with is a specific, closed-in geometric shape, a polygon on our graph. Every single coordinate floating inside that specific unshaded shape is a valid mathematical solution that obeys all 4 of those complex rules simultaneously. So we can draw lines, we can test points, and we can find overlapping regions. That's fantastic. But how do we apply this abstract shape-drawing math to the messy, complicated real world? Or more importantly, to those massive word problems at the end of your paper? Section 5. Real-world linear programming, from words to graphs. This is where the magic happens. We are going to turn complex word problems into the exact visual coordinate systems we just learned to draw. Let's define the core concept clearly. Linear programming is a mathematical method for determining a way to achieve the best outcome in a given mathematical model for some list of requirements. To put it simply, it is the ultimate tool for optimizing your decisions when your resources are limited. It tells you exactly what your options are when you can't have everything. Let's look at a classic example. The farmer. Examiners love these. A farmer is deciding what to plant, using C for fields of corn and W for fields of wheat. He has 3 strict limits. First, a contract says he must plant at least 2 fields of corn. At least translates to greater than or equal to, so C is greater than or equal to 2. Second, he needs at least 2 fields of wheat, so W is greater than or equal to 2. Finally, he only has a small farm. He can sow not more than 10 fields in total. That means corn plus wheat must be less than or equal to 10. So C plus W is less than or equal to 10. Just like that, we've isolated his real-world agricultural limits into 3 crisp, distinct algebraic rules. If we were to draw those out, putting corn on the x-axis and wheat on the y-axis, we draw a vertical line at 2, a horizontal line at 2, and a diagonal line connecting the tens on both axes. We'd shade out the impossible regions. What's left is a triangle of unshaded, perfect possibilities. Any whole number coordinate inside that triangle is a working farm strategy. For instance, 4 fields of corn and 4 fields of wheat. 4 is greater than 2, the other 4 is greater than 2, and 4 plus 4 is 8, which is less than his 10-field maximum. It's a perfect, mathematically proven, viable solution. Now, what's really interesting is how we handle ranges. Let's look at a taxi firm managing its morning fleet of cars, which we'll call X, and minibuses, which we'll call Y. They know they'll make at least 5 car trips, so X is greater than or equal to 5. But look at the minibuses. They expect between 2 and 8 trips. This creates a compound inequality. Y is greater than or equal to 2, but less than or equal to 8. On a graph, this would be 2 horizontal solid lines, creating a visual corridor. Finally, they only have enough drivers for a maximum of 12 total trips, so x plus y is less than or equal to 12. By graphing this, the dispatcher can instantly see every possible valid combination of vehicles they need to prepare for the morning rush. Let's look at one final highly complex set of conditions. This is Antonio the mechanic, and this is a classic high-mark scenario. He mends cars, C, and repairs electronics, E. He works a maximum of 40 hours total. He has a quota, at least 16 hours on cars, so C is greater than or equal to 16. Another quota, at least 5 hours on electronics, so E is greater than or equal to 5. And here is the trap. His boss demands he spends more than twice as much time mending cars as repairing electronics. More than twice as much. That means C must be strictly greater than 2 times E. Notice there is no or equal to there. It's a strict boundary. If Antonio tries to guess his schedule in his head, he's going to mess up and violate his contract. But by taking 60 seconds to graph these 4 lines, he creates a visual map of every single legally compliant work week he could possibly have. We can visualize and solve absolutely any set of rules. From decoding simple greater than symbols to mapping out the schedules of mechanics and farmers, you now understand the mechanics of linear programming. It takes the overwhelming variables of life and traps them on a piece of paper so you can make the smartest possible move. Think about your own study schedule. What invisible constraints are limiting your daily decisions? And more importantly, how would they look if you graphed them? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.